Can sound travel in space? If not, how do astronauts communicate? This version goes deeper into physics, includes real-world space communication systems, and integrates both wave theory and quantum field understanding while still keeping it clear and immersive like a story. Let's begin. Why space is silent and how astronauts still speak. The ultimate physics explanation. Silence. Among the stars, imagine you're orbiting 400 kilometers above the Earth aboard the International Space Station. Outside your helmet, there's nothing but stars and silence. A fellow astronaut is nearby. You see them banging a tool on a metal rail. But even though the collision is powerful, your ears register nothing. Why? Because space doesn't carry sound. And this isn't just poetic. It's pure physics. Let's break it down, layer by layer, until every physical law and phenomenon behind this cosmic silence is fully understood. What is sound, really? Mechanical wave. Physics sound is not a substance, nor is it energy traveling on its own. It's a mechanical disturbance, moving through particles in a medium like air, water, or solid material. In physics terms, sound is a longitudinal mechanical wave. It propagates by causing particles in a medium to vibrate parallel to the direction of the wave. These particle-to-particle collisions create regions of compression and rarefaction, what we perceive as sound. On Earth, when you speak, your vocal cords vibrate. They compress air molecules. These compressions ripple outward until they reach someone else's eardrum, which vibrates in response. But this entire chain requires particles. Without particles to compress, no wave can travel. What is space? The physics of a vacuum space is not empty in a philosophical sense. It is a physical vacuum. According to modern physics, a vacuum has extremely low particle density. In interstellar space, you might find 1 atom per cubic centimeter. Near Earth's orbit, it's more like 105 to 106 particles per cubic meter, still millions of times less dense than air. That means the mean free path, average distance a particle travels before hitting another, in space is so vast that particles essentially don't interact, so in space there's no particle chain to pass a sound wave forward. No matter how hard something vibrates, the vibrations can't move anywhere. The wave dies. The sound never travels. Then, how do astronauts talk in space? If space doesn't carry sound, how is it possible that astronauts have conversations during spacewalks? Here's where physics gets beautiful. Step-by-step breakdown. Step 1. Inside the helmet. Inside the astronaut's helmet is pressurized air. When they speak, sound behaves just as it does on Earth. Their voice vibrates the air, and these pressure waves are detected by a microphone inside the helmet. Step 2. Conversion to electrical signal. The microphone turns these sound waves into electrical signals, a process known as analog to electric transduction. Step 3. Transmission via electromagnetic waves. These electrical signals are used to modulate radio waves, a form of electromagnetic radiation. These waves are transmitted through space using an antenna on the suit. Here's the key. Electromagnetic waves do not need a medium. They are self-propagating oscillations of electric and magnetic fields. They can travel in a vacuum because they're solutions to Maxwell's equations in empty space. Step 4. Reception and sound reconstruction. The receiving astronaut's suit has an antenna too. It captures the radio signal and converts it back into an electrical signal. A speaker inside the helmet turns it into sound waves again, which vibrate the air inside the helmet and reach the astronaut's ears. This isn't sound traveling through space. It's data carried by electromagnetic waves, then reassembled as sound locally. The physics that makes this possible sound is a mechanical wave requires medium, governed by Newton's laws of motion. Energy propagates through interparticle collisions. Radio wave is an electromagnetic wave travels through vacuum, governed by Maxwell's equations. Self-sustaining wave generated by oscillating electric and magnetic fields. Mathematical insight. Electromagnetic waves satisfy the wave equation in a vacuum. Where is the electric field vector? Is the speed of light? Is the Laplacian spatial variation? This shows that electromagnetic waves don't need particles to propagate. They move by field oscillation, not particle interaction. But NASA releases space sounds. Aren't those real? You might have heard eerie recordings like Juno capturing Jupiter's magnetic field, or Voyager's plasma music. Are these real sounds? Not exactly. They are non-acoustic plasma waves, or radio emissions, or magnetic field oscillations. These are not sound waves but data recorded by instruments like plasma wave detectors. Scientists then use sonification to map these signals into human hearing range, effectively letting us listen to invisible forces. Real-life systems used by astronaut suits use ultra-high frequency UHF radios, frequencies between 300 MHz and 3 GHz, high reliability, low power consumption. Modern EVA, extravehicular activity, suits contain digital transceivers, low gain, omnidirectional antennas, redundant communication channels, biometric feedback integration. These systems are tested under Faraday conditions, thermal vacuum and radiation shielding standards. Resulting question is that what physics teaches us sound is not forbidden in space. It's just physically impossible in most of it. And yet, through the brilliance of physics, we convert mechanical waves to electromagnetic waves, send them across the vacuum, and reconstruct voices miles above the Earth. It's not just communication. It's a victory of electromagnetism over silence. Closing words. So, when you stare into the night sky and imagine a world where astronauts float silently among the stars, remember, in that cold, airless void, physics does not allow their voice to travel. But thanks to electromagnetism, electronics, and human ingenuity, they still speak, and someone still listens.